Hey everybody, it's Miss Moran and I'm back to talk to you about our second half of our geometry unit. If you remember before spring break, we worked with parallel and perpendicular lines. We talked a little bit about quadrilaterals and special names for triangles and talked about different kinds of angles. The second half of this is going to be on identifying line symmetry and working with geometric patterns. We're going to test at the end of this week. So the first thing we're going to look at is if we can identify lines of symmetry and can we draw them and how many are there. So a line of symmetry is going to be a line that can split a figure into two mirror images of one another. This is going to have a vertical line of symmetry because I'm able to split this right down the middle here, and I have two reflected images that are congruent, same size, same shape, same angles. We're actually going to use mirrors here so we can see if I put that right down on my line and I look at that, I can see the other half of the figure. Then when I look over it, I see now that's what it's supposed to look like. And then when I open it up, I see that same figure. If we try to do a horizontal line of symmetry, you see that doesn't work. That's not what the figure looks like. The figure looks like that at the top, not like that. All right, so this would be a vertical line of symmetry. This one, I'm not going to be able to split this, even though it sort of seems like it splits it into two parts of the figure. They're going to have to be equal and congruent pieces. So this one's going to have a horizontal line of symmetry. If I were to fold it on this line, this part right here would sit right on top of this here. We'd have an obtuse angle sitting on top of an obtuse angle, acute angle sitting on top of an acute angle. Okay, so those would be two lines of symmetry. So we're going to have a bunch of different figures and we'll be trying to find and draw lines of symmetry. But one thing that we're going to focus on is regular polygons. And we haven't used this word regular yet, although I've kind of alluded to it last week. A regular polygon is going to be any polygon that has all equal length sides and all angles of the same degree. Kind of what you think of when you think of your triangle. Your regular triangle, it's going to be your equilateral triangle. And What's nice about this is when you see a regular polygon, the number of lines of symmetry is going to be equal to the number of sides that are in the figure. And it's kind of a good little trick because most students will recognize this right away and they'll call that one line of symmetry. They'll say it has one vertical line of symmetry. Since these figures are equilateral and balanced all the way around, if we turn our paper, we're going to see that exact same triangle again. And we're going to go from the vertice through that opposite side like we just did. Okay, and then I can keep turning it. So I basically have the same figure rotated 3 times, and I'm going to end up with 3 lines of symmetry. And again, a lot of students wouldn't notice that right off the bat. They'll usually pick one there. For the square is a regular polygon. It has 4 equal length sides and 4 right angles. This is going to have a horizontal. It's going to have a vertical, I said that backwards, horizontal and vertical, and 2 diagonal lines of symmetry. So this is going to have, I'm going to draw that last one very well, sorry about that, 4 lines of symmetry in a 4-sided regular quadrilateral. Okay, again, this is a great trick because most students will recognize this right away and say it only has a vertical line of symmetry. This is a regular pentagon, all equal length sides and 5 obtuse angles. But if we turn this again, we'll see there's another one from that top vertice through the opposite side. Okay, here's another one. Okay, so so my 5-sided figure is going to have 5 lines of symmetry. All right, and again, hexagon, most students will pick 2 here. They'll find those 2 and say I can split this horizontally and vertically. Sometimes they'll even come up with kind of an X here, but they sometimes forget that they've gone from side to side, and you can do that 3 different times. So you can go side through an opposite side, side through an opposite side, and then I can also go from these diagonals to the opposite diagonal like I did on this that first horizontal line. You get them all? Okay, I got them all. All right, so there's going to be 6 lines of symmetry and a regular 6-sided figure. All right, and then with the octagon would be 8. 4 side to sides and 4 vertice to vertice. I'll save the time in even having to draw those and knowing that shortcut that a regular polygon is going to have the same number of lines of symmetry as it has sides. All right, I'm going to do a few of these over here. These are some common misconceptions, and these are kind of ones that always seem to show up on the test. How many lines of symmetry are in the rectangle? Well, students are used to doing the square. They see it's got a vertical and a horizontal, and they want to put the diagonal in there. Okay, these are not lines of symmetry on that diagonal. If we use my mirror there, and I put that on the diagonal, you're going to see that it doesn't make the other half of the rectangle. The reason is if I have, I'll go over this a little bit darker. If I were to fold this over that line, it's another definition of line of symmetry, that you can fold it about a line and it's going to match on the other side. These are two equal size pieces. They are congruent pieces, but they don't line up opposite of that line. Right here we have an obtuse angle. I'm sorry, we have a right angle here and a large space. And when we fold this over the line, it's not going to fit over here. We have a very small space right here. So all of this has to fit here, not fit way over here. And here you've got a large space up here, which is not going to fit in a small space down there. So those are not lines of symmetry. There are only two in the rectangle, a vertical and a horizontal. Okay, the rhombus. Students want to do this all the time for some reason. They want to just split it right down the middle because they say, well, it's an equal length figure. I'm basically splitting it in half. And if I were to take this piece, cut it, and rotate it, it would fit on there. So it does split it into equal sized pieces, but they're not reflected images of one another. I put my mirror down on top of that. You can see that doesn't form the other half of the rhombus. The rhombus is supposed to look like that. It's basically going backwards. Okay, but it does have lines of symmetry, but they're not through the sides. They're through, they're through the vertices, through the corners. So if we go that way, that's a line of symmetry. If we go that way, that's a line of symmetry. So there are two lines of symmetry in the rhombus, but they are not this one. Okay, and then the parallelogram. The parallelogram, similar to the rhombus, but also kind of like the rectangle, and it has these long sides. So if this vertical line didn't work here, it's definitely not going to work here. If I were to split this here, I've got an acute angle, which is not going to match up over here with an obtuse angle. And if I split it this way, I've got an acute angle here, which needs to sit on top of something up here, but there's empty space. So that doesn't work. Again, the vertical doesn't work, and if the diagonal didn't work in the rectangle, it's not going to work here. So even though it does fit it into two congruent pieces, if I rotated it, it is not a congruent piece. This large space right here is not going to fold and fit over something right here. It's got a tiny little space here. It's not going to line up. Okay, so these are some of the trickier ones. Most students are pretty good at picking out, like hearts and butterflies and arrows and shapes like that that have a line of symmetry. But we'll look at it in some of our polygons also. All right, the next thing we're going to get into is geometric patterns. And looking at basically three different types of problems. One would be a pattern that repeats itself. So large square, large circle, small circle, large square, small square, large circle, small circle. So this pattern is going to repeat. So I've got two and two and two and two of different sizes repeating from the square to the circle. Now what makes this a fourth grade question, not a kindergarten question, is not, what comes next, but it might be what are the next, 3 figures in the problem, or what is the 20th figure in the pattern. So if I were asked what is the 20th figure in the pattern, instead of having to draw this out for 20 times, I could see that after every 4, the pattern is going to repeat. So I sort of think of my multiples. And this would be 4, another one would be 8, 12, 16, 20. So the 20th figure is going to be the same as this small circle. So that's kind of another way of applying algebra to it, making it a little bit more challenging. Repeating patterns are going to be the simplest of any of the patterns that we do. Other ones we'll look at are going to be what I call building patterns, patterns that kind of build on themselves and get bigger and bigger. So this starts with triangle, square, and then it's 2 triangles, 2 squares. 3 triangles, next would come 3 squares. So again, they might ask, what are the next 4 figures in the pattern? Or, you know, what is the 20th figure in the pattern? They might have to draw those out or something like that that shows that they're understanding how that builds. All right, and the last one, this is definitely a lot more algebra. This is finding a rule for the pattern. So first you have to identify what's happening, and these are called terms here. So in the first term, I have 1 circle. In the second term, I have 3. In the third circle, I have 5. In my fourth figure, I have 7. And in my fifth, I have 9. And a lot of students will look at this pattern and say, oh, it goes from 1 to 3 to 5 to 7 to 9. So our pattern is that we're adding on 2 each time, which is true. But that doesn't tell us what the rule is for any number term in the figure. If my question is how many dots would there be in the 8th figure, I don't want to have to skip count 1, 3, 5, 7, 9, 8 times. I want to get in a picture in my mind of how is it built, and is there a rule? Is there a way I could figure this out without having to draw out the 6th and the 7th and the 8 terms? I'll take a look here. So this looks like my starting pattern here. So I've got 1 circle there. So how is this one different? What's happening here? Well, I have that same circle here, but I'm also now making it a height of 2 and also sort of a length of 2. So I'm adding 1 to the vertical and 1 to the horizontal. In the third figure, I'm adding 2 more, but I have 3 in the vertical and 3 in the horizontal. Okay, for this one, I've got 4 in the vertical and 4 in the horizontal, and 5 in the vertical and 5 in the horizontal. So it seems almost like we're just doubling the number of the term. You know, in the fourth figure, I've got 4 high and 4 wide. In the fifth term, I've got 5 high and 5 wide. So it's kind of like we're doubling it, but not really, because this is a double counted circle. So really what I have, if I were to look at this, is whatever figure, whatever term I have, I call that the nth term. So if I were to multiply that times 2, so 2 times the number of the figure, but I'm going to subtract 1 because I'm really double counting that first starting spot. So this would be in my 8th figure, my 8th term, I would have 8 high and 8 wide. So 8 times 2 is 16, but not double counting that one there would be 15. So I'd have 15 circles in my 8th figure, and I know what it would look like too. 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's 15. I didn't have to count them. I've used math there to figure that out. All right, here's another example. This is, again, a pattern that kind of builds on itself. So we're looking at this. I've got 2 circles here to begin with. So in the first term, it doesn't really make a whole lot of sense. I'm looking at my second term. What is different here? I've got 2 rows of 2 and an extra circle here on the top. My third term has 3 rows of 3 and an extra circle on the top. My fourth term has 4 rows of 4 with an extra circle on the top. And my fifth term has 5 rows of 5 with an extra circle on the top. So how many would be in the 8th pattern? Well, that would be 8 rows of 8 with an extra circle on the top. So whatever number term I'm using times itself plus 1 extra. It's a way of applying algebra to it. So if I did the 8th figure, I'd have 8 times 8 is 64, plus 1 more. I'd use 65 dots. And I don't have to draw that out. I'm just using patterns and logic and algebra to determine that. All right, so thank you so much for watching. Don't forget to review what we did before spring break on lines and shapes and quadrilaterals especially. And then we will have our test this week on Friday, including line symmetry and geometric patterns.